In this lesson, we will be discussing quadratic functions and models. First of all, let's take a look at what a polynomial function is. A polynomial function f of degree n is given by this equation. So we have f of x equals a sub n, x to the n, plus a sub n minus 1 times x to the n minus 1, all the way down to a sub 1x to the 1 plus a sub naught, okay? And all of these coefficients, the a sub n minus 1, and the a sub 1, along with our constant term a sub naught, all are real numbers. A sub n cannot be 0 because that would yield a 0 for our leading term. Okay, so now that we know what a polynomial function is, we will take a look at the cases for n that we have. So we'll start with n is 0. So if we have a degree 0 polynomial, it is a constant function. An example of that constant function would be like f of x equals 2. If we were to graph that, we would get a horizontal line going through the point 0, 2. The leading coefficient is understood to be 2 because we have 2x to the 0 power. The next type of polynomial we have is a linear polynomial function. It is of degree 1, so x is to the first power. A concrete example of that would be f of x equals 5x minus 1. Our leading coefficient is 5. Okay, increasing the powers, now we have a quadratic function. So an example of a degree 2 function is given here. We have f of x defined to be 4x squared minus x plus 1. We can see there that our leading coefficient is 4. Okay, in the next example, we have a cubic polynomial function. It is written here. You can see that it is degree 3 with a leading coefficient of 2. And then finally, we will consider here the quartic case where we have a polynomial of degree 4. Okay, the leading coefficient here is understood to be a 1 because there is a 1 understood right there in front of x to the 4th. Okay, and so we're going to dig in here now with quadratic functions. So quadratic functions are of the form f of x equals ax squared plus bx plus c. A, b, and c are all real numbers. A cannot be equal to 0. Okay, so when we think quadratic, we think degree 2. The most basic quadratic function would be f of x equals x squared. If you were to make a table of points and plot them, you would get this graph, which is the graph of a parabola. The domain of that graph is negative infinity to infinity, and the range is 0, infinity. Okay, and so as we mentioned, the graph is called a parabola. Parabolas are symmetric with respect to a line. That line is called the axis of symmetry, or simply the axis. It is here the axis drawn by the dotted line, and the point where the axis intersects the parabola is called the vertex. Okay, the vertex can be the lowest point on your graph if the parabola opens up, and the vertex would be the highest point on your graph if the parabola opens downward. Okay, we can apply graphing techniques to quadratic functions. So if we have the function f of x equals x squared, we know now what that looks like. So we can use our knowledge of transformations, translations, reflections, etc. to generate a graph of a polynomial f of x in this form. So we know at the heart of the function is a quadratic because this is of degree 2. Okay, all of the other values around it just indicate which way we're going to shift our quadratic. So again, at the heart of the function is the square. So x squared, I see that. Okay, now if you go inside the function, all right, and you add or subtract a value, okay, Okay, here that's given by h. So if you add or subtract, it will move the graph right or left. Outside the function, if you add or subtract here, it will move the function up or down. And then finally, we consider what is sitting outside the function right here, this value a. So if a is positive, then the graph is going to open up. If the value for a is negative, the parabola is going to open downward. And then we look at the value for a. If the absolute value of a is greater than 1, then the graph is stretched and the graph is shrinks if a is a fractional value between 0 and 1. Okay, so keeping that in mind, if we write a function in that form, in that vertex form, we can then graph by using transformations. So what we're going to do here, we are going to use the process of completing the square. We're going to then plot points to determine our graph. So to complete the square, we are going to gather our quadratic and linear terms, and we're going to put the constant value out to the side. To complete the square, we need to take half the coefficient of our linear term, right? Square it and add it inside. So we're going to take half of -4. We get -2. Then we're going to square that value to give 4. That is the value that we're going to add right here. Now, to keep the function balanced, we don't want to change it. So by adding 4, we're changing it. We need to balance that out. So because we added 4, we're now going to subtract 4 to keep our function unchanged. So we get f of x equals x minus 2 squared minus 6. So at the heart of the function, I see x squared. So we know what x squared looks like, all right? It would be a parabola with the vertex at the origin, okay? But for this function, the vertex is not going to be at the origin like it is for x squared. It is going to be shifted. So remember, if you're inside the parentheses and you add or subtract a value, you're going to move left or right. In this case, since it's a -2, that means we're going to shift it to the right 2. Okay. So that vertex is going to move right 2 from 0. This -6 here indicates a downward shift of 6. So we're going to move our graph down 6 units. Okay. So in doing so, we get the location then of our vertex. So our vertex is at 2, -6. Okay, we know that our graph opens up. We know that because the coefficient here, our value for a, is 1. So it's going to open upward. Now the easiest way to go about finishing our graph is to find the y-intercept. The y-intercept occurs when x is 0. So the y-intercept is simply -2. So we can plot 0, -2. That's our y-intercept. And in doing so, we get this part of our graph. Okay. We can use our axis of symmetry, which is that vertical line that goes through our vertex. We can use that to finish the graph out, to get a symmetrical part of the graph on the right. Okay, and so that is our parabola there. If you wanted more points to kind of firm that graph up, you certainly could. You can find x-intercepts, and that would make your graph more accurate, or any points that you wanted to get. Let's look at another one. Now this function g of x equals -1/2 x squared is a parabola. We know that it is because it is a quadratic. It's x squared, so we know the general shape. So we're going to look here. We know that the function has not been shifted left or right any, because if we were to kind of look at this in a different form, we can see that we haven't moved left or right any, we haven't gone up or down any. So we are still, when we graph the parabola, we are still right here at the origin. Right? So that is going to be our vertex. That is 0, 0. And now we're going to go about determining another point on our graph. First thing to note is that there's a negative out front. That tells me that the parabola is going to open downward. Okay? The 1/2 tells me that I am going to be shrinking my graph by a factor of 2. I can go ahead and substitute some values in to get points on my graph. So if I let x be 1, I have negative 1/2 times 1 squared, which is negative 1/2. So I have 1 comma negative 1/2. Make this a little bit better here. Okay, and so our graph is just going to be wider than that of y equals x squared. The domain is negative infinity to infinity. The range is negative infinity comma 0, okay, with a bracket. Okay, another example here, we are going to kind of analyze it the same way. All right, so we have at the heart of our function a quadratic x squared. So we know that we're dealing with a parabola. So now we just need to look at how we're going to shift our graph. Here we know that we're going to shift our graph right because there's a negative in there, so we're going to go right 4. And here we're going to go up 3. So the vertex for x squared is at the origin, but keep in mind that here we are going to be moving away from the origin. We're going to be moving to the right 4 units, and we are going to move up 3 units. Okay, so that's going to put my vertex right here. So my vertex then is going to be 4, 3. Okay, there's multiple ways to proceed from here. We can analyze in different ways. First of all, I know that the quadratic here, since it has a negative out front, that the parabola is going to open downward. So that's certainly one piece of information that I can make use of. I could find the x and or y intercepts to proceed, right? Or I could just plot some points. So there's different avenues to take here. I am going to find the y-intercept. Okay, so to find the y-intercept, I'm going to let x be 0. So I have negative 1/2 times 0 minus 4 squared plus 3. So that's negative 1/2 of 16 plus 3. So that would give me negative 8 plus 3, which is negative 5. So 0, negative 5 is my y-intercept. So I have my axis, I have my vertex, and another point. And so that's really, all I need. Based on symmetry, I can go ahead and graph the other side. Okay, so again, not the only way, but it is a way to go ahead and get that graph. The domain is negative infinity to infinity. The range is negative infinity, comma, 3 with a bracket. Okay, and so now let's look at how to graph by completing the square when we have a coefficient on our quadratic that's other than 1. So here we are going to group our quadratic and linear terms as we did before. We leave our constant out there to the side. Okay. Now what we're going to do is we are going to factor out that negative 3. So we have negative 3 times x squared plus, and then we have 2/3 x plus 1. Okay, and so now we are going to complete the square. We take half the coefficient of that middle term, so half of 2/3, which would give us 1/3. Then we're going to square that 1/3, and that'll give us 1/9. So that's the value that we add right here. Now here's where the hang up comes in. We are not really adding 1/9 because we have a -3 out front. So really we're adding -3 times 1/9. That would be -1/3. And so because I have a net loss of -1/3, I'm going to have to add 1/3 over here to keep my function unchanged. So rewriting f of x, I have f of x equals -3 times x plus 1/3 squared plus 4/3. Okay, and so then we can use our knowledge there of transformations to move that around. And we can also find the intercepts of the graph. Okay, so let's go ahead and do that. Get a graph going. So at the heart of our function is the quadratic x squared. I know that that would be centered at the origin. Okay, but here we are shifting to the left 3 and to the left 1/3, sorry, and then up 4/3. So we're going left 1/3 and up 4/3. So that's going to be my vertex. Okay. Now, because there's a negative out front of the quadratic, right? Or you could look at it up here, whichever's easiest. We know it's going to open down. So we can go ahead and proceed knowing that. That's one piece of information. I can find the y-intercept by letting x be 0. When I plug in a 0 for x, I get 0, 1, right? So here's this other point. I have 0, 1. So that is going to be my y-intercept. So at 0, 1, I have -1/3 and 4/3. Those are some points there that I have on my graph. Now, if I wanted to go ahead and graph it, I could, right? Because I have my axis of symmetry. I have this part of the graph, okay? And that will make it complete. So I could just stop right there, but since in this problem we were asked to identify the intercepts, we're going to go ahead and do that. We have identified the y-intercept, but to identify the x-intercept, or intercepts, I should say, we are going to let y be 0. So we have 0 equals -3x squared minus 2x plus 1. That is a quadratic equation, so different ways to tackle that. I'm just going to shift the terms over to the left, so I have 3x squared plus 2x minus 1 equals 0. And then I'm going to factor. If it's not factorable, then I would just use the quadratic formula. So here, by trial and error, I have 3x and x plus 1 minus 1. Okay, and so then we know that our x-intercepts are 1/3. So 1/3 comma 0. Right here, that's 1/3. And then my other x-intercept is -1. Okay, so now we're going to talk about kind of a shortcut for finding the vertex. So we have used the method of completing the square. Instead of doing that, you can look at what happens in the case where you complete the square on this general form of the quadratic equation. If you were to complete the square abstractly, then you would get these equations that result. H, right, which is the x-coordinate of the vertex, that's given to be the opposite of 2a, and k is f of h. So again, the vertex is given by hk. Remember, that tells us how much we've shifted to the right or left or up or down, okay? So our new vertex is given by hk. And we can plug in these formulas, and we don't have to complete the square in that case. So if we have this equation, okay, and we're asked to find the axis and the vertex, we can apply those formulas that we just learned, okay? So we know that the vertex is given by hk. This h is the opposite of b all over 2a, and this k is just going to be f of h. So let's go ahead and figure out what that is. So we know a is 2, b is 4. So we're going to plug in. We have the opposite of b all over 2 times a. So that's going to be negative 4 all over 4, which is negative 1. So h is negative 1. Now to find k, I'm just going to plug 1 into f. I need f of h, which is f of 1. So I'm going to plug in 1 in my function wherever I see an x. So I have 2 times 1 squared plus 4 times 1 plus 5. And let's see, that comes out to be 2 and 4, which is 6, and 5 makes 11. Okay. So my vertex is given by negative 1, comma, 11. Okay, now the axis we know is given to be the vertical line that goes through, right, that vertex. So it would be simply x equals negative 1. Okay, so the axis, all right, is found by just looking at the x coordinate and setting that equal to negative 1 to indicate that we have a vertical line. So our axis is x equals negative 1. Okay, and so finally, the last thing we're going to talk about are quadratic models. Okay, so here, if air resistance is neglected, the height, s, in feet of an object projected directly upward from an initial height, s sub naught feet, with initial velocity, v sub naught feet per second, is given by this general function. Okay, so this is a quadratic function because we see the 2 in the exponent position of our variable. T is our time, that's our independent variable. S is our height, that's our dependent variable. Now, the v sub naught and the s sub naught are constants. So these right here are constant values, and they're going to depend on the application. So if you're working an applied problem, the v sub naught and the s sub naught are given quantities. So let's apply this. Let's say a ball is projected directly upward from an initial height of 100 feet with an initial velocity of 80 feet per second. We want to write a function that describes the height in terms of t. So remember, the height is s of t. Okay, t is my time, so that's my independent variable. The initial height here, let's go back to our formula. The initial height is given by s sub naught. So it's going to be here what we label. So we have s sub naught, and the velocity, the velocity is 80 feet per second, and the initial height is 100 feet. Okay, and so now let's go ahead and write our model. So we have s of t equals negative 16 t squared plus 80t plus 100. So that answers that question, and now we can use that model to make predictions, answer questions regarding height of the object as it relates to time. So let's say we want to know after how many seconds does the projectile reach its maximum height, and what is the max height? Okay, so the maximum height is the vertex because this is a quadratic, And so you have a projectile that goes up and comes back down. So this max height right here is the vertex. So if you're asked to find the maximum height, you simply need to find h and then k. All right. So h will give you your time, and then the k will give you the corresponding height. All right. So we want h is the opposite of b all over 2a. Going back to our formula, remember b is 80, okay, and then a is negative 16. So we have the opposite of 80 all over 2 times negative 16. So that gives me negative 80 all over negative 32. So we'll punch that into our calculator here, and I'm getting 2.5. So we have 2.5, and we're working with seconds. So the maximum height is going to occur after the projectile has been in the air for 2.5 seconds. Again, that gives us the time. We want to know also the maximum height. So the answer to the first part of the question, after how many seconds does the projectile reach its max height? The answer is 2.5. Now we're going to answer this second part. So what is the max height? The max height is given by k. That is f of h. So we want to find f of 2.5. So in our function f, we're simply going to replace our function t in our function with 2.5. So we have negative 16 times 2.5 squared plus 80t plus 100. Okay, so we're going to plug that in our calculator and see what we come up with. Okay, so that ends up being 200. So the max height is going to occur at 200 feet.